Extreme values. Alright, before we get started, we're going to do a quick review of intervals and interval notation. So suppose a and b are real numbers. Then a closed interval has the notation with closed brackets around the endpoints a and b. And the closed interval means that we include the endpoints a and b. So graphically what this means is that the closed interval ends with closed points. So that corresponds to this picture over here on the bottom left. So I have this closed interval on this particular image from -1 to 2, because at -1 on the function I end with a closed point, and at 2 I end with a closed point. As opposed to an open interval, with interval notation having open parentheses instead of closed brackets, open intervals do not include endpoints. So graphically they end with open circles. So that corresponds to this middle picture here. So from -1 to 2, we have open circles at the end of the interval. We include all the points in between. So the only points not included are the endpoints at 2 and at -1. And then finally we can have what's called a half open or a half closed interval, where one side is an open parentheses, meaning there's an open circle there, and the other side is a closed bracket, meaning there's a closed point on that side. So they include one or the other endpoint, and graphically one closed and then one open circle. So that corresponds to this last one. So the closed endpoint is at -1 and the open endpoint is at 2. Okay, so now we can define extreme values. So extreme values, or extrema, and the singular version of this is extremum, of some function f of x are the maximum and minimum values of the function. And so extreme values can actually split up into two different categories. So what we can have is we can have absolute extrema and we can have local extrema. Now there's two different words here because either of these can be used synonymously. So we can hear absolute or global extrema, or we can hear local or relative extrema. So let's first take a look at absolute extrema. So we're going to let f of x be some function defined on an interval I, with a some number in that interval I. We say f of a is the absolute minimum of f of x on the interval I if f of a is less than or equal to f of x for all x values in the interval I. So this is a really formal way of stating this. Here's what we're really saying. So we need some function f, and we need to take a look at that function on some interval I. Now there's an asterisk here. Typically, I is the entire domain of the function. So we're looking at the function either on a smaller interval or the whole domain. Then if a is in that interval, f of a, the y value, is considered a minimum if f of a is less than or equal to all the other function values. So the easier way to think about this is the absolute minimum is the smallest y value on the original interval I we were taking a look at. And then the absolute maximum is, well, the opposite. So the absolute maximum of f of x on I is this value f of a, where now f of a has to be greater than or equal to all the other function values for any x value in that interval we choose. So the absolute maximum is the biggest y value on the interval I. So informally, absolute minimum, smallest y value, absolute maximum, biggest y value on the entire interval. And sometimes that interval is smaller than the domain, sometimes it's the entire domain. So now, local relative extrema, we say that f of x has a local minimum at x equals c if f of c is the minimum value of the function f on some open interval containing c. So this is a little different because informally a local minimum or local minimums are the y values at any valley in the graph. So we can potentially have more than one local minimum, and what we're looking for is still y values. So all extreme values we're talking about y values unless otherwise asked for. So we're looking at any valley in the graph and what is the smallest y value in that valley. And local maximums occur at a particular x value if f of c, that y value, is the maximum on some open interval containing c. So local maximums are the y values of any peak in the graph. So we're looking for the biggest possible y value at any mountain region. So we're looking for valleys and we're looking for peaks for local minimums and local maximums. So there can be more than one. As opposed to an absolute minimum or an absolute maximum, it's just the biggest y value or the smallest y value. And all of these have to be real numbers. So in other words, we cannot ever classify a min or max as infinity or negative infinity because those are not real numbers. Alright, so now let's make this a little more concrete by looking at an example. So given the graphs of f of x, identify any absolute extrema and any local extrema. So we have two different graphs here. Each of these are the graphs of f of x, the original function. So we're going to look at each one separately, and we're going to try to identify absolute extrema and local extrema. So there are four different categories here. I can have an absolute maximum, I can have an absolute minimum, and then I can have a local max, or I can have local maxes potentially, and local mins. So when the problem is asking me to identify absolute and local extrema, I have to take a look at all four of these different potential categories. So now, absolute maximum. So by definition, we're looking for the biggest possible y value. Now we're not given any interval here, so we're going to assume it's over the entire domain. So the entire domain of this quadratic is negative infinity to infinity. So is there any one particular biggest y value? So what we're looking for is the highest peak in the graph. So hopefully we can see that that happens right here at this point, at the coordinate point 2, 3. But the maximums and minimums, extreme values, unless otherwise asked for, are only the y value. So the max point is happening up here at 2, 3, but the maximum value, what's the biggest y value that comes out of this graph, is 3. So the absolute maximum is 3. Another way of writing that, because I'm calling this the function f of x, is to say f of 2. But because we know the actual y value, it's better that we list that value as 3. So now let's attempt to find an absolute minimum. Is there any smallest y value? Is there any lowest valley in the graph? So here's an example of where, since these arrows on the bottom indicate that this graph goes down forever on both sides of the function, there is no smallest y value because these are heading towards that y at negative infinity, which is not a real number. So for absolute minimum, we are going to say there is none. So we're actually looking for a peak in the graph, or I'm sorry, a valley in the graph for a minimum, and there is no valley. So there's just y values that get smaller and smaller and smaller and smaller, heading towards negative infinity, but I cannot say that that's the minimum because that's not a number. So now local maximums. So again, we're looking for now all potential peaks in the graph. So there may be more than one. Now in this case, there's only one peak in the graph. There's just this one peak that we saw earlier when we looked for the absolute maximum. So the local maximum as well is the y value 3. Or again, we can classify that as f of 2 if we want to. So we would classify the local max as 3 as well, even though it is also the absolute maximum. It's just that potentially there could have been more maxes on this graph locally, but in this case there's not. There's just the one. So local minimums, there are no valleys in the graph as we discussed, so this one also has none. So now taking a look at this right graph, we're again trying to find all four categories. So we're trying to find an absolute max, an absolute min, any local maxes, and any local mins. So for absolute, whoops, this mins. So for absolute maximum, we're looking for potentially the biggest peak in the graph. Well, this graph is sort of the opposite of this one because this one goes up to infinity forever. So the biggest y value is not a real number. This goes up to positive infinity, which is not a number, so absolute maximum on this graph, there is none. And so absolute minimum, we're looking for the smallest y value in the graph. So we're looking for any valleys. Well, on this graph, there are two valleys, here and here. So the lowest valley, the smallest y value, is going to happen at this coordinate point here, which let's just go ahead and approximate it. It looks like that's maybe about negative 4.25. So again, we're only concerned with the y value, so the absolute minimum of this graph would be negative 4.25. Now, typically, we wouldn't do this so inaccurately by just looking at a graph, but we're just trying to get the general idea for an absolute maximum and an absolute minimum. So the absolute minimum is about negative 4.25. So now local maximums, there was no absolute maximum, but there is going to be a local max. So a local max is any peak in the graph. So there is a peak in the graph occurring right here. There's this little looking mountaintop, and I want to look for the biggest y value in that little peak of the graph. So the biggest y value, looking at the y-axis here, is negative 1. So the local maximum is the y value negative 1. And then the local minimums, because there are two, well, a local minimum occurs where the absolute minimum occurred at negative 4.25. So that's one local minimum. And then the other local minimum occurs over here at this valley in the graph, and we'll approximate that as negative 2.5. So here's a little bit of a different example than the previous one. So it is possible to have no absolute max, but to have local maximums. We can have more than one local minimum. There's a lot of different possibilities based on the shape of the graph. Alright, so now let's answer the question, do all functions have extreme values? So in the last few examples, maybe I didn't have an absolute maximum or an absolute minimum, but I had a local max or a local min. So do all functions have any extreme values? The answer to that, as we'll see, is going to be no. A function doesn't have to have any extreme values. So here are three examples of functions that have no extreme values. So let's try to think about the absolute maximum of this left graph. So since this is a line, this side is going to go up forever towards positive infinity. So there's no biggest y value. And this left side of the graph is going to go down to negative infinity. So there's no smallest y value. And then if we're looking for any local maxes or mins, we'd be looking for any peaks or valleys in the graph. So this linear function here has no peaks or valleys. So this line, y equals x, has no extreme values. So no extreme values at all. Now this graph in the middle is x cubed. So we don't just need to have a linear function to have no extreme values. This is the cubic function, so x cubed. And this also has no extreme values. So the right side goes up forever, and I can't say positive infinity is an absolute maximum. The left side goes down forever, so negative infinity is not an absolute minimum. And there are no peaks in the graph. So we do have this behavior near the origin, but this flattened out behavior, but there is no peak or there is no valley. So this graph too has no extreme values. And then finally, this graph on the far right. So you might be thinking, well, this graph has a peak, but if you'll notice, it's missing the actual function value that's defined at 0. So there's this removable discontinuity at 0. So if I were to try to find an absolute maximum, well, if this point were filled in, then absolutely 4 would be the absolute maximum. But because the function is undefined here, there's no absolute max. Because these two arrows go down forever, negative infinity is not a real number, so there's no absolute minimum. And then again, there's no local maximum either, because again, this potential point that would have been a local maximum is missing. And there's no valleys in the graph, so there are no local minimums. So again here, no extreme values. So we can also have different types of functions that have no extreme values whatsoever. Alright, so now let's take a look at this theorem, which tells us that if we have a function that is continuous on a closed interval from a to b, then that function has to have both an absolute maximum and an absolute minimum. So we had found previously 3 examples of functions that had no extreme values, so this theorem gives us a condition upon which a function has to have an absolute maximum and an absolute minimum. So when does it have to happen? When I have a continuous function defined on a closed interval. So remember, closed interval meaning it contains its endpoints. So let's think about that linear function again, y equals x. And that was not a closed function. That function went off to positive infinity and negative infinity. So the domain was negative infinity to infinity. Let's go ahead and just take a portion of that function y equals x. So I'm going to go ahead and define it to go from, let's say, negative 4 to, we'll say, positive 4. So I'm going to attempt to draw a straight line here. Alright, not too bad. So here's the function y equals x, but now y equals x is defined on this closed interval from negative 4 to 4, including the endpoints. So that previous function was an example that did not have an absolute maximum and minimum, but now this function that stopped and was defined with closed endpoints, a closed interval, this does have an absolute maximum, the absolute maximum being 4, the biggest y value is 4, and the smallest y value is negative 4. So the difference is the closed endpoints. And of course, this being a continuous function, so this linear function is continuous. So I could go ahead and say that my absolute max of this graph is the y value 4, and the absolute min is the y value negative 4. Alright, so now I'm going to draw a different looking graph that's still continuous on a closed interval. So I'm going to go ahead and start this graph right here, and then make it look something like this. So I'm closed at each endpoint. So this is at an x value of 3, and this is at an x value of negative 4. So I have a closed interval. Both ends are filled in circles, and this was continuous. I drew the whole thing without lifting my pencil. So on this particular graph, there is an absolute maximum. So there is a biggest y value on this function. It is happening what looks like up here on my sketch at, let's say, 5.5. So my absolute maximum on this graph is at 5.5. And my absolute minimum, well, I am including the endpoints here. So the smallest y value of the endpoint is going to be down here at negative 2. So my absolute minimum occurred at the endpoint value, y value of negative 2. So the biggest y value is 5.5, and the smallest y value occurred at the left endpoint at negative 2. So one thing that I want you to observe on this graph on the right-hand side is that the absolute minimum occurred at an endpoint, but the absolute maximum occurred at a place with a horizontal tangent line. So at this particular x value at 0, if I were to draw a tangent line, that tangent line would be horizontal, which means that the derivative at that location would be 0. So I want you to keep that in mind as we go to the next definition. Alright, so far in our study of extreme values, a lot of it may have seemed familiar up to this point because we've been analyzing extreme values given the graph of the original function f of x, and that's a pre-calculus problem. So now we need to start introducing how calculus fits into this equation. And where it starts to fit in, how we're going to find extreme values using calculus, is first looking for the critical points or the critical values given some function f of x. So if we have a number c in the domain of f, that number c is called a critical point or a critical value if either f prime of c equals 0 or if f prime of c does not exist. So the typical terminology we're going to hear is critical point, even though that's a little bit flawed because a point is of the form x comma y, And you'll notice that we just said a number c is a critical point. So we're actually only going to be concerned with the x value. So even though we're going to ask you for critical points, it's kind of a flawed way of saying it because we're only asking you for the x value. So I don't actually want your answer to be a coordinate point, just the x value of the coordinate point. So to find these critical points, the process is going to be, we're going to need to set the derivative f prime of x equal to 0 and solve for x. And we're going to have to find all the x values where the derivative is undefined, if any. So to find where a function is undefined, we set the denominator equal to 0, if possible. So if there's no denominator, there's not going to be any places where the derivative does not exist. And now, one of the really important things to remember is that these numbers have to be in the domain of the original function. So once we set the derivative equal to 0 and find where the derivative is undefined, we have to just double check that those x values are in the domain if they can be plugged in to the original function and still make sense. So there's no vertical asymptote there or a hole in the graph there, so that they're not in the domain of the original function. Alright, so here are some examples of finding the critical points for each of the following. So here's my original function f of x. So to find the critical points, we find the derivative. So f prime of x, using the power rule, we're going to get 6x minus 6. So we want to find where this derivative is 0 or undefined. So since this is not a rational function, there's no denominator, I'm really just going to take this derivative and set it equal to 0 and solve for x. So if I add the 6 to the other side, and then if I divide by 6, I'm going to get this x value of 1. So x equals 1 is my critical point value. So again, as I said, it's kind of a flaw in the notation because we would stop here and say that 1 is a critical point. So even though, is a critical point. So even though a point is generally an x and a y, I'm only concerned with the x value. So just 1 is a critical point. Taking a look at the next example, g of x equals x to the 2/3. So we need to find the derivative. So I have 2/3 x to the negative 1/3. And I want to find where this is 0 or undefined. So when I have x raised to the negative 1/3, this is the same as moving x to the negative 1/3 to the denominator where this 3 is. So this is 2/3 x to the positive 1/3 is my derivative. So there's no places where the derivative equals 0. That's setting the top equal to 0. And 2 can never be 0. But the denominator can be 0 when x is 0. So 3x to the 1/3, if I set the bottom equal to 0, well, this is only true if I let x equal 0. So if I technically divide by 3 and then cube both sides, I will get x equals 0. So on this problem, I want to make sure that 0 is in the domain of the original function. So does it make sense to plug 0 back into the original function? And it does. I can take 0 to an exponent. It's always just going to be 0. So 0 is in the domain, so 0 is a critical point. Now on the first example, if you're wondering why I didn't plug the 1 back in to check it, hopefully you recognize that this is a quadratic, so the domain is all real numbers. So any number that I got out as a critical point is in the domain because everything is in the domain. So now finally, for the last one, I have to take the derivative, so h prime of x. I have to use the quotient rule here, so low d high minus high d low over low squared. So now on the numerator, I will distribute the 2x to the x and the minus 3, so I'll get 2x squared minus 6x minus x squared over x minus 3 squared. So the numerator, the 2x squared and the minus x squared become one copy of x squared, and then I have minus 6x and then x minus 3 squared. So in order to find places where this derivative is 0 or undefined, I'd have to set both the top and the bottom equal to 0. So where the top is 0 is where the derivative is 0, Where the bottom is 0, that's where the derivative is undefined, or the derivative does not exist. So if I set the top equal to 0, x squared minus 6x equals 0, I can factor out an x here, so x times x minus 6 equals 0, and use my zero product property, set each of these terms being, or expressions being multiplied equal to 0. So I have x equals 0, x minus 6 equals 0, so I get x equals 0 and x equals 6. And then in the denominator, the only value that will make the denominator equal 0 is positive 3. So now it's a matter of going back and checking that 0, 3, and 6 are in the domain of the original function. The only number that's not in the domain of the original function, the only number that creates a problem with the original function, is positive 3. Because at positive 3, there's a vertical asymptote. Positive 3 will make the denominator 0. So that means x equals 3 is not a critical point. So 0 and 6 are critical points of the original function h of x. Alright, so now let's look at Fermat's theorem on local extrema. This says that if f of c is a local min or max, then c is a critical point of f. So what we need to do, or what I want to do, is I want to draw a picture that satisfies the hypothesis being the if part. So if f of c is a local min or max, so what I've drawn over here on the left is a graph that has a local min and a local max. So let me highlight those. So here I have a local min at this valley. So right about here, I have a local minimum. And then over here, I have a peak in the graph. And one that I haven't seen before, one that happens at a sharp turn, but it's still a peak in the graph. It's still a biggest y value that occurs over a particular interval. So it's still a peak in the graph that's occurring. So this function has a local min and a local max. Then Fermat's theorem says that c is a critical point of f. So f of c is the y value. So the y value at this coordinate point here is 2. But what this theorem is telling us is that, well, because 2 is a local max, then the number it came from, which happens to also be 2, is a critical point of f. So if we know that there is a y value that's a local min or max, then the x value it came from is a critical point of f. So I know that 2 is a critical point from the fact that positive 2, the y value positive 2, made this a local maximum. And then down here, this minimum that occurs at negative 4, whatever the x value that came from here that made this function go to negative 4 is also a critical point. So that happens over here at negative 3. So this coordinate point is negative 3, negative 4. So the x value that corresponds to this local minimum is going to be a critical point. So 2 is a critical point and negative 3 is a critical point because we had a local min and a local max at these two different locations. So notice what's happening on the graph at each of those locations. At this particular point, at this minimum, I have a horizontal tangent line. So I had a place where the derivative equals 0. So in other words, f prime of negative 3 right here equals 0. So by definition, negative 3 is a critical point. And up here, I have a sharp turn. So f prime of 2 does not exist. So f prime of 2, or at 2, the function is not differentiable. So again, by definition, a critical point is occurring at 2. So the second thing I want to talk about in regards to this theorem is that it doesn't work the other way around. So if a y value is a local min or max, then the x value it came from is a critical point. But it's important to know, down here, if c is a critical point, the function does not necessarily have a local minimum or maximum at c. So this graph on the right is the counterexample to the converse being true. So this bottom part, if C is a critical point. So right here at 0, I have a critical point on this graph of x cubed. So this is the graph of x cubed. It's going to be our counterexample function. Right here at 0, there is a horizontal tangent line. So what's true? It's true that 0 is a critical point. But notice, we talked about this particular function having no extreme values. So even though 0 is a critical point, f of 0, that y value, is neither a min, a local min, or a local max. So it only works in this direction. If a y value is a local min or max, then C is a critical point. But if C is a critical point, such as in this function 0 is, f of 0 does not necessarily have to be a local min or max. Alright, so the goal for the rest of the section is going to be to try to find extreme values on a closed interval. So assume that f of x is continuous on the closed interval from a to b, and let f of c be the minimum or maximum value on a to b. Then c is either a critical point or one of the endpoints a or b. So what this little theorem is telling us is that the maximum and minimum values have to occur at either critical points or endpoints on a continuous closed interval. So here are two functions f of x that are both continuous on closed intervals, and we're just going to show that the maximum and minimum, so absolute maximum and absolute minimum, have to be at an endpoint or critical point. So on this first graph, we have an absolute minimum occurring right here at this lowest peak in the graph. And notice that this x value that this minimum occurs at would be a critical point on the graph because there is a horizontal tangent line right here at this valley in the graph. So the absolute minimum occurred at a critical point, whereas the absolute maximum value occurs up here at the end point. So the biggest y value over this entire closed interval happens to be up at this y value of 6. So on this graph, the minimum, absolute minimum, happened at the critical point, and the absolute maximum happened at an endpoint. So we're going to have to check both when we start to get to our examples. So here's just a second example. On this one, the absolute maximum occurs at a critical point, so a horizontal tangent line. Here's my absolute maximum, so at whatever this x value critical point would be, and the absolute minimum also corresponds to a different x value, so we'll call that x2. So x1 and x2 are critical points. The absolute max happens at the y value that corresponds to x1, and the absolute minimum corresponds to the y value that goes with x2. So this tells us that in order to find the extreme values on a closed interval, the minimum and maximum, and notice we drop the word absolute. So when you don't see any word local or absolute associated with min or max, it's assumed it's absolute. So to find the absolute min or absolute max, we're going to have to check both the critical points and the endpoints, because that's where they can occur. So now here's a series of steps for finding extreme values of a continuous function on a closed interval a to b. So the first step is find the critical points of the function by determining where the derivative is 0 or undefined. And then what we're going to need to do is calculate the function at the critical points and at the endpoints. So in other words, substitute each critical point into the function, provided that those points are in the interval that we're interested in, and then substitute the endpoints a and b into the function. And then in part 3, we have to determine which is the largest and which is the smallest y value from our answers in parts 2a and 2b. And then finally write out the absolute max and the absolute min as a y value. So this asterisk says to find extreme values on an open interval, because this is all pertaining to a closed interval. To find extreme values on an open interval, we're basically going to skip step 2b, because there are no endpoints on an open interval. Alright, in this first example, we want to find the absolute max and min of the function 2x cubed minus 15x squared plus 24x plus 7 on this closed interval from 0 to 6. So you'll notice off to the right here, here's a graph of this function strictly on x values from 0 to 6. But this would not be typically given in this problem. I just wanted to give this so that it corresponds to all the information we're finding and to really enforce the concept of what we're doing. So based on this graph, we can see that the absolute maximum is going to happen at the endpoint. So it's going to happen at f of 6. And we can see the absolute minimum is going to happen at a critical point over here at around 4. So let's go ahead and show that rigorously by following the steps and finding the critical points. So we have to find the derivative to find the critical point. So the derivative of this function by the power rule is going to be 6x squared minus 30x plus 24. And we're going to need to set this equal to 0 because it's not going to be undefined anywhere. So before I set it equal to 0, I'm going to factor out the 6. So I'm left with x squared minus 5x plus 4. And I want to set that equal to 0. So now I'm going to go ahead and factor this quadratic. I can pretty much ignore this 6 on the outside because I can divide both sides by 6. And this right side, 0 divided by 6 would be 0, and that gets rid of this 6 over 6. So now this factors to x minus 4, x minus 1. So by the zero product property, I could set each of these equal to 0, x minus 4 and x minus 1. So my two critical points are x equals 1 and x equals 4. So those are my critical points. Now I should do a quick check to make sure they are both inside the interval, and 1 and 4 fall in this interval from 0 to 6. So now the next step would be to substitute these critical points into the original function. So we would have to substitute 1 into f and 4 into f and find the corresponding y value, and we'd also have to substitute in the endpoint, 0 and 6. So we're looking for the biggest and the smallest y value to find the absolute max and absolute min. So plugging in 0 is no problem, so I'm plugging them into this original function. So if I were to plug in 0 for each of these x's here, well, these three terms involving x would go away, and I would just be left with the constant 7. So f of 0 is 7. And to find these other values, while I could do it by hand, just substitute 1 into each of these terms, substitute 4, substitute 6 separately, I'm going to go ahead and give you the numerical answers. And on a problem like this, because again, this is sort of more of an arithmetic concept than it is a calculus concept, plugging in these values could be done using your calculator and storing this function as the y1 function and evaluating it at different numbers. So these are all the values for f of 1, f of 4, and f of 6. They are 18, -9, and 43. So now we need to summarize our results. 43 is clearly the biggest number that came out, so 43 is the absolute max, and -9 is the smallest number, so that's the absolute min. The absolute max is just the y value, 43, and the absolute min is just the y value, -9. And that's it for the first example. Alright, in the next example, find the maximum of f of x equals 1 minus the quantity x minus 1 to the 2/3 on the closed interval from -1 to 2. So this problem is just asking us to find the maximum, and although they didn't say absolute maximum, it is implied. So we need to find the critical points of this function and test the critical points and the endpoints of the interval from -1 to 2. Now again, here's the graph of what's happening between -1 and 2, and although this would not be given, by looking at this graph, it tells us that our absolute maximum, it looks like it occurs at an x value of 1, and the absolute maximum looks like it is the value 1 itself as the y value. So let's go ahead and verify that by doing the work analytically. So we'll have to find the derivative, f prime of x. The derivative of 1 is 0. The derivative of this requires a chain rule, so I'd have to bring the 2/3 to the front, so I'd have -2/3 x minus 1. If I reduce the power by 1, I get to the -1/3, and then the derivative of the inside I would multiply by, but that's just 1. So now I need to find where this is 0 or undefined. So what I'm going to do is rewrite it so I don't have this negative exponent. So I have a negative 2 on the top, I have a 3 on the bottom, and this whole term, x minus 1 to the negative 1/3, would move to the bottom and become x minus 1 to the positive 1/3. So there are no zeros, but there is a location where this function is undefined, and that location is at x equals 1. So if I set the bottom equal to 0, 3 times x minus 1 to the 1/3 equal to 0, so I can divide by 3 and I'd get x minus 1 to the 1/3 equals 0. And then I could take the cube root of both sides, or I'm sorry, I could cube both sides. So if I cubed both sides, 0 cubed is just 0, and that gets rid of the 1/3. So add the 1 to the other side, I just get out 1, which you didn't have to show all this work. We can just get that by looking at this. This has already been factored, but just to show the steps. So x equals 1 is a critical point, but I should be a little concerned when I find critical points when I set the denominator equal to 0. We have to make sure that that number is in the domain of the original function. Critical point, sorry. So if I plug 1 back into the original function, is that part of the domain? Does it make sense? And it does. I can plug 1 in right here into this x. I'd get 1 minus 1 minus 1 to the 2/3. So I'd get 0 to the 2/3, which is just 0. So I would get out the real number of 1. So 1 is in the domain. So 1 is a critical point, which we can see that it is, and this is a place where the derivative is undefined because I have this sharp turn. So now I'd have to test this function by plugging in the endpoints, negative 1 and 2 and 1 into the original function. So I want to find f of 1, f of negative 1, and f of 2, and find the biggest value because I'm only looking for the maximum in this problem. So let's do this one by hand because the numbers are pretty small. So if I were to substitute in 1, I kind of already did that when we checked whether or not 1 was in the domain. Remember, we get 1 minus 1 minus 1 to the 2/3, or 1 minus 0. So I get out 1. When I substitute in negative 1, I get 1 minus, I get negative 1 minus 1 to the 2/3. So I get 1 minus negative 2 to the 2/3, and then let's plug in 2 before we keep going to see what happens. So we're going to get 1 minus 2 minus 1 to the 2/3. So I would get 1 minus 2 minus 1 is 1. So 1 minus 1 to the 2/3, 1 to the anything, any number is going to be 1. So this is 1 minus 1, so this is 0. So far I can tell that 1 is bigger than 0. So now it's just a matter of which one is bigger between these two values here. So it's a matter of trying to determine whether or not 1 minus negative 2 to the 2/3 is bigger or smaller than 1. Well, we just have to reason to ourselves that this quantity is smaller than this one, which we can, again, we know we're aiming for that because we have the graph, but in general, we don't really know that. So we have to convince ourselves of which number is bigger between the two. So this is a property of exponents that I want to review. So if I have, let me just bring it over here, negative 2 to the 2/3, that's the same as negative 2 squared, and then that whole quantity raised to the 1/3. So negative 2 squared is positive 4, and now I have positive 4 to the 1/3, which I can't take this to be a whole number. So I cannot take this is equivalent to the 3rd root of 4. But here's what I do know, that the 3rd root of 4 is a positive number. So if I take a positive number and subtract it from 1, it's definitely going to be smaller than 1. So that forces 1 to be the biggest output value that came out from testing the critical point and the endpoint. So 1 is the absolute maximum, is the conclusion for this particular problem. So there's a little bit of reasoning here that went into this if this was a non-calculator problem, in trying to decide whether or not between these two quantities which one was the biggest. So 1 is going to be the biggest, and it does correspond with the graph. Alright, in this next example, find the x values of the absolute max and min of f of x equals x squared minus 8 natural log x on the closed interval from 1 to 4. So similar to what we've done in the past two problems, but this one is asking me to find the x values of the absolute max and min. And this function also includes the natural log of x, which is going to give us a different type of derivative that we're going to need to simplify before we can find its critical points. So let's go ahead and find the derivative. The derivative of x squared is 2x minus, now the derivative of 8 natural log of x, 8 is a constant, so we'll ignore that for a second. The derivative of natural log x is 1 over x. So if I multiply 1 over x times 8, my derivative is 8 over x. And I would need to find where this is 0 or undefined. So here I have this linear function 2x minus this rational function 8 over x. So what I need to do is I need to find common denominators and turn this into one rational expression. So I can set the top and bottom equal to 0. So I cannot leave my answer like this to find my critical points. I have to combine. Once I have one fraction, I have to turn it into, or once I have a difference involving a fraction, I have to turn it into just one fraction. So I'm going to multiply the top and bottom of this left side by x to force common denominators. So 2x squared over x minus 8 over x. So since they have common denominators, I have 2x squared minus 8 over x. So now to find where the derivative is 0, I set the top equal to 0. So 2x squared minus 8 equal to 0. And then I set the bottom equal to 0, so just x equals 0. So now I have to solve this. You could add the 8 to the other side and divide by 2. I'm actually going to factor out the 2 to be left with x squared minus 4 equals 0. And the 2 I can ignore because I could divide by 2 and get rid of it. So I'll get x minus 2, x plus 2. So I get positive 2 and negative 2 as my critical points. So I have 2, negative 2, and 0. And so now I want to check my interval, and the only one that falls in that interval is positive 2. So negative 2 and 0 do not fall in the interval from 1 to 4, but more than that, 0 and negative 2 are not in the domain of the original function. So natural log of 0 doesn't make sense. The natural log function cannot substitute in 0 or negative numbers. So 0 and negative 2 are also not in the domain of this function as well, so they could not be critical points. So only negative 2 is. So my next step is to substitute in the endpoints 1 and 4 and the critical point 2 into my original function. So I have f of 1, f of 4, and f of 2 to find. Now f of 1 is a value I can find by hand, so I'm going to do that one by hand. I have 1 squared minus 8 natural log 1. Now natural log of 1 is a quantity you should know. That value is 0. So this is 1 minus 8 times 0, or 1 minus 0, so f of 1 is 1. So now what I have to do is find f of 4 and f of 2. And for those values, I'm going to go to my calculator and tell you that they are 4.909 and negative 1.545. So we can see that the biggest value that's going to come out of this function over these three different values is 4.909. So this is going to correspond to my maximum, and negative 1.545 is going to correspond to my minimum. But now I have to go back and just be careful because the problem asked me to write the x values of the absolute max and absolute min. So I'm actually not concerned with these specific decimals that came out. I'm concerned with the x values we had to substitute in to get out these numbers. So I'm going to go ahead and write this as the absolute max occurs at x equals 4. So the max occurred at the x value of 4, and the absolute min occurs at the x value of 2. So that does correspond to our graph. We can see the absolute maximum happening at the end point over here at 4, and then the absolute minimum happening at the critical point that we found, which is 2. Alright, in this last example, I want to find the min and max, so it's implied the absolute min and max of f of x equals sine x times cosine x on the closed interval from 0 to pi. So similar type of problem to what we've been doing. The only difference is this involves trig functions, which is what makes it a lot more challenging for students, but it's something we're going to have to get past because there's a lot of trig coming up in this chapter and in future sections. So the unit circle is something you should absolutely be familiar with from your previous classes. So let's go ahead and start this problem by finding the derivative. So f prime of x is going to require a product rule. I have sine x times cosine x. So the first function, sine x, times the derivative of cosine x is negative sine x, plus the second function is cosine x, times the derivative of the first function, the derivative of sine is cosine x. So what I have here is I have two copies of sine x, so I have negative sine squared x plus cosine squared x. And I'm going to have to set this equal to 0. So to solve a function like this, first of all, this left side is not 1. Unfortunately, this negative in front of sine squared x blocks that Pythagorean identity for us. So what I have to do to solve this is I'm going to add sine squared x to the other side, so that what I'm really in search of is when does cosine squared x equal sine squared x on the interval from 0 to pi. So on the interval from 0 to pi, meaning on the unit circle in quadrants 1 and 2. So here's 0 and here's pi on the unit circle. So when does cosine squared x equal sine squared x? Well, what I can do is find when does cosine x equal sine x. And in fact, because both quantities are squared, I can even find when does cosine equal sine, and then when does negative cosine x equal sine x. So in other words, at what angles do I get the same x and y value, but one can be positive and one can be negative? So without really going into too much trig, because that's a lot of review, this happens at pi over 4 and at 3 pi over 4. So this coordinate point on the unit circle is radical 2 over 2, radical 2 over 2. And this coordinate point is negative radical 2 over 2, radical 2 over 2. So in other words, if I at each of these angles, if I square both of these, they're the same quantity, because if I square a negative, it becomes a positive. And then here, they're already exactly the same value. So at the angles pi over 4 and 3 pi over 4, I have places where cosine squared x equals sine squared x on the interval from 0 to pi. So my two critical values are then pi over 4 and 3 pi over 4, which, if you see the graph again, it wouldn't be given. It does correspond to where I'd have two horizontal tangent lines on this particular function. So now I have to test the critical points, pi over 4 and 3 pi over 4, and the endpoint 0 and pi in the original function. So I have to do f of 0, f of pi, and then f of pi over 4 and f of 3 pi over 4. So let's go ahead and substitute in 0. If I have sine 0 times cosine 0, sine of 0 is 0, so 0 times anything is 0. F of pi, so I have sine pi, cosine pi, and sine pi is 0, so again we have 0. So now substituting in pi over 4, I have sine pi over 4, cosine pi over 4. So radical 2 over 2 times radical 2 over 2, knowing each of those values on the unit circle, when I multiply across, the radicals cancel. I get 2 over 4, so I get positive 1/2. And then if I substitute in sine of 3 pi over 4, cosine of 3 pi over 4. So 3 pi over 4, we have this from solving this original equation. So if I have sine of 3 pi over 4, sine is the y value, so that is positive radical 2 over 2. And cosine is the x value, which is negative radical 2 over 2. So it's going to be the same number, only negative, so negative 1/2. So between all four of these results, the biggest value is positive 1/2 and the smallest is negative 1/2. So my absolute max is 1/2 and my absolute minimum value is negative 1/2. So just as straightforward in the setup as all the other problems, the difference is being able to solve a trig equation of this form where I really truly have to understand the unit circle, and then being able to evaluate trig functions on the unit circle as well. So you've reached the end of this 3-part video, and now I have a very serious set of warnings. This chapter contains many different rules and tests and theorems. Some are introduced in a collection of methodical steps to follow, but to only memorize these steps without understanding the concepts, that will leave you lost and confused by the end of the chapter. And, as with most topics in calculus, this collection of topics and concepts carries over into the next few chapters. In this chapter specifically, I want to remind you of the rule of 4. You must understand all of the concepts presented analytically, so that means with symbols and variables, graphically, which is why I additionally presented you with the graph over each particular interval, numerically, so that's substituting in the values, being able to find and compare which value is bigger, which is smaller, without a calculator, and finally, verbally and in writing. So most, if not all, questions require that you explain your answer. So this goes to the verbally and in writing portion of the rule of 4. You must be extremely specific in your explanations as to which function you are referring to. And you may never, ever use the word it in your explanations, or you will not earn any credit. Explanations in this chapter, they need to be detailed and reference the appropriate theorems where applicable. Finally, writing must be extremely legible. I'm not going to try to guess what your answer is, and neither is the AP grader. So this is a chapter that is full of concepts, in other words, so to only memorize the steps, because I will provide you with a set of steps to follow, but to only memorize these steps is going to hurt you in the long run. So this is the chapter where I really want to stress that you go and try to understand the concepts of what's happening, understand every problem in these 4 ways in order for you to be successful in this chapter and going forward into next semester.